Let's now consider one example of how you may conduct experiments on comparing the performances among algorithms. And what will be the idea, first of all? So the idea would be, so once the algorithm, since you want to run it on the computer, you must be fully implemented and ideally maybe tested first before you can run it to really compare. Because if you compare one correct algorithm against another incorrect one, it doesn't make sense. You want to make sure before you compare the algorithms, they are all correct. Idea would be you want to execute the fully tested program on test inputs of various sizes and structures. Remember the two criteria that we spoke about. You want to make sure you actually conduct the experiments by running the algorithms on different input sizes and structures, so that you actually got a full picture. You got a complete picture about how these algorithms may vary on different scenarios. And for each test, you want to record the elapsed time of the execution. So this is really the key, because since we talk about time efficiency, you want to see exactly which algorithm may run with the least time, for example. So this will be the skeleton of the Java code you may write. So remember, long is the data type for integer, right? It's we just want to make sure the time the time stamp you actually try to store actually got enough storage. So we got a start time, we also got end time. And the idea would be you simply want to calculate the difference between the gap between end time and also start time. And how do you calculate the start time and end time? You simply we can use some Java system library. So the system class actually got a static method called current time in milliseconds. So that's the method. And that this method call here is going to return back to you some long like an integer value. And this method call, this second call to the same method is going to give you also another integer. For example, this and it's always the case that end time should be strictly larger than start time. There must be at least 1 millisecond of gap, at least. So for example, this may be 5 and this may be 10, in which case what will be the gap? 10 minus 5, which will be 5. So that means the execution of your algorithm will actually take 5 milliseconds, right? Hopefully you can get an idea. And we're going to use this skeleton of code to actually conduct certain experiments. And upon the completion of the various test runs, you may also want to visualize the results, just maybe, for example, by plotting some graph, which I will show you as well. And to really make some sound statistical claim, meaning that if you really want to conclude like which algorithm will actually be the most time efficient, you want to make sure you really compare the candidates, all the alternatives, all the available alternatives actually on the various sizes and structures of the inputs. Otherwise, maybe one algorithm is simply only good at a particular scenario but not others. So in order to make any conclusive claim, you really want to make sure you test for as many scenarios as possible. Right, so that's basically what this sentence really concerned about. And let's now consider this example experiments together. And let me switch to my iPad notes over here. And the problem that we want to compare, computational problem, remember we got to specify the input, the output, and also the relation between the input and output. So the input here is simply just a single character and also another integer n. So there'll be two inputs. One is a character, the other one is an integer. Okay, and then what will be the corresponding output? The output will just be a string, right? That's the output. But what about the relationship between the input and output? The output is going to consist of n repetitions of character C. For example, if you give the two inputs star and also 15, the corresponding output should be, you want to repeat the star for 15 times, right? It's rather straightforward what we are supposed to do. And we got two candidate algorithms, two implemented methods for us to consider. Algorithm number one, use the string concatenation operation, which will be the plus equal one, mainly the plus, right? If you recall what you learned from the first year, so when you say answer plus equals C, that's equivalent to answer is assigned to answer plus C, right? That's something I want to remind you quickly. And you simply run a loop from 0 until, well, that's rather straightforward. You want to repeat for exactly n times, right? And then you want to construct a new string, answer plus equals C, accumulate C for every iteration, and then eventually return the result, right? And the second algorithm over here is actually going to use the string builder class, which is part of the Java API library. You can go to the API page and explore further if you wish. But we're going to run the same number of iterations as well. But inside the body of the loop, we're going to only call the method append over here, and then append the C to the end of the string builder. So you can see what I highlighted over here in yellows is exactly where the difference is between these two algorithms. Now, I may just want you to have some intuition. Which algorithm will be more efficient time-wise? You can pause the video and think about it. All right, assuming that you thought about it. So the answer is this version over here is way more efficient, as we'll see some statistical table. But before that, I just want to visualize to give you some idea about what's going to happen at the runtime. Okay, let's start with this one here. Let's say answer is plus equals C, right? As I said before, is equivalent to answer is assigned to answer plus C, right? That's it, what it is equivalent to computing. So what's going to happen is, imagine that if answer is already is a string, it's a reference type. So answer is pointing to some string objects, right? Let's say string object. You can think about string is it's simply an array of characters. Let's say you simply got this many character in the string objects. Okay, so that's the answer. And the right hand side over here, answer plus C. Especially we are using the string concatenation operator over here. So how do we calculate the right hand side over here? How do we do that? In order to do that, what Java would do is it's going to create some intermediate result before we can assign that back to the answer, right? So what's going to happen is we're going to do this string concatenation, but in order to do it, we have to make a copy of the answer. We have to make some intermediate objects. So what's going to happen is we're going to duplicate this string. Of course, this duplicate is only hidden. It's only temporary. As soon as the concatenation is done, it's going to be discarded. You don't really see that. You cannot really manipulate it as a programmer. So whatever string it is, okay, conceptually. So this will be the left-hand side and then concatenated with C. So you can think about C is also going to be added over here. So once it is done, you're going to reassign answer to this intermediate result. So answer, rather than pointing to over here, it is going to point to over here. So that's what's happening. Okay. On the other hand, what about this string builder solution over here, right? You can think about there's also a reference type. So SB is pointing to a string builder object over here, right? This is how you visualize an object's string builder. Okay, and then it has maybe some attribute called value over there. That one there also got an array of characters. Okay, let's say currently that's what you have so far, and you want to simply append a single character to the end. And for that one there, it is not going to actually create intermediate and hidden objects. It is not going to. What you would do is simply just going to append C to the end. Sorry, I'm just running out of space, but I'll just put C over here. Okay, you can think about it should be to the right over here. Okay, so once we got this C appended, and that's done, right? So now, can you see the fundamental difference between these two? The fundamental difference is for the algorithm number one, it takes way more space to compute, because every time you actually want to append, you want to concatenate into a particular string, you also need to make a copy of that. So that will definitely take memory space, and the copying itself will also take some time. On the other hand, for the append over here, every time for the string builder, you simply append to the end. So that's the fundamental difference between the algorithm. So it takes more space to copy, and at the same time, it will take more time. All right, let's now go back to the slides and let's see some result for the experiments. Right, so these are the two algorithms I just explained. And let's see the statistical table. Repeat number one is the one using string concatenation, which uses more memory. And repeat number two actually uses the string builder append, which doesn't use any extra intermediate memory. Let's say we try to repeat some character for 50,000 times. And in this case, it's in milliseconds that we talk about, right? Remember the elapsed time that we spoke about in the earlier slides. In the case of string concatenation, we use this much milliseconds, and for the case of the string builder, we use this much. Even though it's already about 3,000 times much, but we cannot really tell the difference because it's only milliseconds. So we'll still consider both algorithms to be fast. Let's now try to double the input size. So rather than 50,000, it's now 100,000, right? 100,000 repetitions for the character. You can see roughly from here to here, it's about 3 to 4 times, right? For the running time over here, and here it stayed the same. But sometimes, but you may have to look at many rows in order to see the general pattern. Let me go a little bit faster. So let me again double the time. Double the size of the input. So it's now 200,000. You can see go from 7,000 to 39,000. It's about 5 or 6 times, right? And this one is only about 2 times. Go from 1 to 2. You can kind of see the pattern already, I hope. Let's double the input size again. So from 200,000 to 400,000, right? And then we go from 39,000 to 170,000. Again, about 5 times. And we go from 2 to 3, about 2 times maximum. All right, let's keep going. All right, and then you can see this keep growing, and the magnitude in the milliseconds is really something that we can definitely notice. We can notice the time that will take between this algorithm and also this algorithm. We can definitely see. Eventually, I want to show you this particular result. You can see this is the ultimate input size over here. In that case, it will take about 3 days for the string concatenation algorithm. And it will only take about 135 milliseconds for the repeat number 2 that uses a string builder to complete. Right? You can see, so we can see it's definitely the definite winner will be repeat number 2, especially when the input size grows very large. Not really infinity, but it's still runnable. It should still be runnable by our computers. All right. So the input size, you can see the row here. From row to row, the input size is simply doubled. But one thing to note, even though this particular running time is very huge, but you should really see the relationship between this and this, right? Every time we double the input size, how has the running time changed? That's something we want to observe as well. And I will give you the conclusion, right? For repeat number 1, every time we double the input, so go from here to here, or to go from here to here, or go from here to here, is roughly about 5 times of the increase of the running time. Whereas, in the case of the repeat number 2, it's about 2 times. For example, you go from 28 to 58. It's about 2 times, right? So that's the kind of visualization we can actually make. I can also show you some plot in the next slides. But this is really some statistical summary you have to make if you want to conduct physical experiments. You can see it's kind of should be a very rigorous process you want to follow through. Otherwise, you cannot really make a very sound claim. All right, so that's the plot over here, the graph. This is repeat number 1 over here that uses string concatenation, and this is repeat number 2 which uses the string builder. One very important facts to note: both of them are simply so-called linear function, meaning that you can define each one of them like a y is equal to f of x, right? In this case, it's roughly the rate of change is about, as we said before, it's about 5. So this will be y is equal to 5x roughly, and the blue one over here will not be as steep. So this one will be roughly y is equal to 2x. Okay. Remember, we actually talk about the rate of change over here. So that will just simply correspond to the slope of the two functions over here. Okay. And then, but as we will actually see later in the module, so these two functions mathematically or especially asymptotically will be considered as in the same family. So they are both linear function. Right, let's now talk about the challenges, like why this physical experiment is actually may not be ideal for the purpose of this course. Okay, let's see why. So we got 3 reasons for that. Let's go over one by one. Reason number 1, in order to really run the algorithm on your computer to really calculate the elapsed time, you have to make sure the algorithm is fully implemented, and also it should be fully tested. Otherwise, you're not really comparing correct algorithm against correct ones. But what if our purpose is only to really choose among many alternatives? Maybe we're designing new algorithm and we just want to have an idea about which ones we want to choose. But sometimes it may not be worth the time for you to invest to actually implement the code, because you still have to implement it in Java and also write some JUnit test cases for that, and also have to debug. It may not be worth your time. It would be very nice just to sketch the solution maybe on the paper. You can still write your Java solution on the paper. It may not be as rigorous process as you have to implement it in Eclipse, but at least you can get some idea about what the running time should be. That would be very ideal. All right, and then also that's really the mini conclusion for this bullet point. Can there be a higher level analysis to determine that one algorithm or data structure is more superior than others in terms of the time complexity, right? You don't really have to fully implement the algorithm to make sure it's correct. We don't really need to bother until we actually make a decision. All right, so reason number 2. Whenever you want to compare multiple algorithms, you actually want to make sure they are run under the same hardware condition, like a CPU type, and also the number of the current workload for your CPU. So there are many factors, physical factors. You want to make sure they are identical. Otherwise, it's not fair comparison. And also, you want to make sure the software is also identical, the operating system. And if you're running Java, you want to make sure the Java virtual machine is also the same version. So these are just some example factors. Of course, it's doable. You can definitely make sure it's exactly the same identical environments you're running the different algorithms in order to compare their performances. But is it really worth the time to ensure such configuration is identical? It may not be if you got many algorithms to really compare. All right. Final points. Experiments can only be done on a limited set of test inputs. After all, you have to really write down the exact experiments to really run in Java. So in that case, sometimes it will be much easier to actually miss some test cases, maybe miss some scenarios. So what if maybe important inputs were not included in the experiments? For example, maybe the experiments you have devised only consider those ideal scenarios for your particular algorithm, without considering those that may cause your algorithm to actually run for a long time. So you're not really considering the worst case scenario for by running the experiments. So that's definitely one example limitation for running physical experiments. On the other hand, if you can actually do certain higher level analysis of your algorithm, in that case, it's much easier to really consider what a worst case scenario might be for the different algorithms. Okay, and that's about the 3 limitations of doing physical experiments. And in the next part of the module, we are actually going to talk about what will be the ideal analysis mechanism to really address each one of the limitations.